Hello everyone. Welcome to the session. I am Seshavidya, working as Associate Professor in the Department of ACE at R.M.K College of Engineering and Technology. So today in this session we are going to discuss Unit 3, that is high frequency lines. So in that we are going to discuss impedance matching at high frequency lines. So let us move on to the next slide. So this is about impedance matching in high frequency lines. So first of all we should know what is impedance matching. So we know that since we are going to use the transmission lines at high frequency level, so here what is impedance matching is, what's the purpose of this impedance matching is. So as we know that using that maximum power theorem, it is necessary to have that source impedance that should be is equal to the load impedance. Only then we can able to transfer the maximum amount of power from source to the load. The same phenomena that can be used here also, that's nothing but impedance matching. The main purpose of this impedance matching is first of all to avoid the reflections, so that we can just transfer the maximum amount of power from one place to the another. So here we are going to use the different methods that can be used to achieve the impedance matching. So there are various methods that can be used for the impedance matching. They are short length transmission lines, single step matching and double step matching. In short length transmission line in the sense, so we'll be using the transmission line sections as in impedance matching section. So by using this transmission line sections, we can able to achieve this impedance matching by equating the source impedance with the load impedance. So in the short length transmission lines, here we can say that the first one is 8th wavelength. That is, we are going to see that we are going to use that matching section with the length lambda by 8, so that it is called as 8th wavelength. And the second type is nothing but L is equal to lambda by 4. So that is the length of the matching section is lambda by 4. We can call it as quarter wave transformer. Suppose if the length of the matching section is lambda by 2, then we can call it as half wave line. So these are all the three methods we can use it under short length transmission lines. The same impedance matching that can be achieved by using the single step as well as double step matching. So first of all, we'll just see that short length sections one by one. So impedance matching using short length transmission lines. As I told you, 8th wavelength in the sense that is the length of the section is lambda by 8. The length of the matching section is lambda by 8. So already I derived that the input impedance of dissipationless line. So there we can just substitute the length of the matching section, that is lambda by 8. So by substituting this lambda by 8, we can just able to see what is the source impedance in terms of load impedance. So here we'll be just substituting that this is our equation, input impedance equation of dissipationless line at high frequency line. So here we're going to substitute this L is equal to lambda 8. So according to this equation, here it is S. So we're going to substitute S is equal to lambda by 8. So in this Q, and Q is nothing but actually we are just denoting in terms of beta. So beta S is equal to, so beta is nothing but 2 pi by lambda and S is nothing but lambda by 8. So we'll be getting it as pi by 4. So instead of this beta S, we'll be getting it as that is pi by 4. So we know that tan of 5 by 4 is nothing but 1. Substituting this, we'll be getting it as Zs is equal to R naught of Zeta plus J R naught by R naught plus J Zeta. Suppose if the characteristics impedance, that is Zeta, is terminated by its characteristics impedance, then this term get cancelled. So finally we'll be getting it as Zs is equal to R naught. So we know that source impedance is equal to the characteristics impedance, then we can call it as an infinite line, which means there is no reflection at all. Why? Because reflection coefficient is 0. So obviously there is no reflection at all. So we can just transfer the maximum amount of power from your source to the load. So next to this impedance matching using quarter wave transformer. So here instead of this lambda by 8, here we are going to substitute lambda by 4. Why? Because the length of the matching section is quarter wave, that is quarter wave length. So S is equal to lambda by 4. Again we'll be substituting in input impedance of dissipationless line. So tan pi by 2, it's nothing but infinity. So we'll be getting it as source impedance is R naught square by zeta. So here the input impedance of the line is equal to the square of characteristics impedance of the line into that of load impedance zeta. So this quarter wave transformer line is that can be chosen by equation Z naught is equal to R naught, and that is also is equal to Zs into zeta. So according to this equation, we can just able to design a quarter wave line. So what is the main drawback in case of quarter wave transformer is that, so this technique needs a special line of characteristics impedance for every pair of resistances that has to be matched. That is the main drawback of quarter wave. So next one we are going to see what are the applications and disadvantage of quarter wave line. So there are three applications. The first application is that, and here it will act as an impedance inverter. That is, we can just able to transfer low impedance to high impedance and high impedance to low impedance. The second application is that it is also used to couple a transmission line to the load. That is, load is in the sense it is an antenna. And third application is that it can be used as an insulator. That is, to support the open wire line, we can just use that quarter wave line. The main disadvantage of this quarter wave line is nothing but it is very sensitive to change in frequency for a new wavelength, and the section will no longer be lambda by 4 in wavelength. This is main drawback in case of quarter wave line. So next one is off waveline. So by substituting S is equal to lambda by 2 in the input impedance of dissipationless line, you'll be getting it as tan pi. So tan pi, we know that it is equal to 0. If you substitute tan pi is equal to 0, then we'll be getting it as Zs is equal to R0. That is the off waveline repeats its terminating impedance. Or we can call it as this off waveline is considered as 1-to-1 transformer. So likewise, we can able to that is a match the source impedance with the load impedance. So by matching both source and load impedance, we can able to achieve the maximum amount of power that can be being transferred from source to the load. So that is the main aim of impedance matching. So thank you for your patient listening. Thank you.